I talked at the end about calculating optimal capability distribution. And there is, in fact, a discipline called capabilities engineering, which even has an ontology of sorts. And you see that we have here people with individual competencies, which is just another word for capability, organizations with organizational capability, and individual competence enables organizational capability, and then organizational capability enables system capability. So a system has a system capability, and then there is more about operational capability and so on. So I think this is very close to the sort of view I have in mind. The next step in the story is as follows. We want to understand how BFO can be used as a basis for understanding the sorts of things that happen in systems and in applying systems to specific projects. So application of engineered artifacts in the systems realm to the typical problems that systems are designed for. Now, as a first step towards understanding that, I'm going to present very briefly an ontology that we created called the product lifecycle ontology. This will illustrate several things. First of all, it will show you how BFO works when you're trying to apply it to an engineering phenomenon. And secondly, it will show you where systems are related or where systems appear in the product lifecycle. So the product lifecycle goes from having a problem, having certain technology, using that technology to engineer, test, and then to manufacture a product. The product gets deployed. There are then operations. So you're flying the airplane, since this is the Air Force Research Lab view of product life cycle. You're supporting the airplane. You're landing the airplane. You're disposing of the airplane at the end of its life. And the whole thing then starts again. You have a new problem, a new kind of aircraft you want to build. You design it. You use the technology. You manufacture. You deploy, and so forth. So that's the product life cycle. And that's BFO. And that's the top level organization of BFO, roughly speaking. And that's another view of the same top level organization of BFO. And that's what we were talking about in the morning. And where function is a special kind of capability, namely, it's the capability that the thing itself was designed to realize. So we have this 4-part list of categories, and we have material entities on the left, which include things like aircraft and engines and sensors and air bases and systems, including an integrated vehicle health management system, which does for diseases what the Roswell Park Cancer Institute does for aircraft what Roswell Park does for people. And attributes are things like quality, function, capability, but also things like cracks and faults. And when we're going to ignore our attributes for the moment and just concentrate on these. So information entities are things like technical manuals, requirement specifications, designs, parts lists, sensor data, maintenance reports, and so on. And then processes are design process, production plan generation process, landing, and so on. So these are the 3 categories we're going to focus on. And now we're going to do the product life cycle by viewing how these categories are realized in time. So we have the general category process. Then we have the child category planned process. That's the processes that you're supposed to realize. And the Air Force has all kinds of plans for deployment of its personnel and its equipment. And the product life cycle is one kind of planned process. And it begins with a design process, and then you have a production plan generation process, then a production process, then a maintenance process, interspersed with a use process when you operate the aircraft, and then followed by an end-of-life process. So we've seen all of this. And now we'll see an information entity. So the production plan generation process has an output, which is a production plan, which is an information entity. And the production plan guides the production process, which has an output, which is a product. And similarly, a maintenance plan generation process has an output, a maintenance plan, which guides the maintenance process. And these arrows, and this is a very sloppy set of slides, as you can see, but the arrows are all pointing in the direction of the all-sum rule. So every production plan generation process has its output a production plan. Every production process is guided by a production plan, and every production plan guides a production process. Remember, this is the planned realm. This is the way things should be. So we have 3 information entities, and we have various processes. But now we have something which is an actual material entity, a product. An aircraft wing has been generated through a production process guided by a production plan and so forth. And now these are more documents. There is a sortie, which is guided by a sortie plan and which has as part a flight. And this is more informational support for the maintenance process. So aircraft maintenance is a really complicated affair. It costs, I can't remember now, $250,000 to keep an aircraft in the sky. And if you have an aircraft in the sky which is going to need a certain widget on the other side of the Pacific Ocean tomorrow, it's very difficult to make sure you get the right widget to be in the right place in order to avoid huge costs, particularly if you send the wrong widget. Then all right, so that's why you have all these documents, and now you have flights, which have flight manuals, and now we get to the systems part. So a production process has output of an aircraft, but the aircraft is part of a system which includes human beings, such as the designers and the machinists and the maintenance engineers and so forth up here. But they are also part of a system which includes things like factories and repair depots and aircraft air bases and energy supply systems and water supply systems and data supply systems and so on. And so these two, and these two, and these two, and these two, and these two, I mean 2 kinds of entities, yellow ones and blue ones. I'm going backwards, that's why it's going wrong. So these 3 now are all in the service of this. So these are the material entities, including the systems, which the product life cycle depends on. People, fuel and aircraft and weapon systems and ammunition and so forth, more people, disposal people, and then a maintenance system, for instance, the vehicle health maintenance system, a fuel supply system, a utility system or a series of utility systems, infrastructure, so transport delivery systems to move fuel and aircraft around and so forth. So this is where systems go. And this is how we are to understand systems from a BFO point of view. They're all material entities. All right. So now let's see if we can use this to do the job of defining system. So only some of the things here are properly called systems, although the whole of what is here, I think, might properly be said to represent parts of one single system with subsystems as parts. And this brings us to the first the point that I wanted to make, which we've already addressed at various points in the course of the day. So systems tend to be embedded within larger systems. And of course, there may be some ultimate largest system, which might be the whole universe, but most of the systems that we've been talking about today are embedded within larger systems. So let's suppose this is a rental car. It has a hydraulic system. Now, auto rental is very complicated. People don't understand the ontological beauty of rental car system. People think that rental car is a service, but it's not a service. any more than car manufacturing is a service. It involves service elements, but it also involves manufacturing elements. So the rental car hydraulic system is part of a larger system, which is the rental car company maintenance system. So that you keep the car on the road and you keep the car hydraulic system functioning because you have maintenance engineers who are in a position to maintain it. If all of them went away, your system would fail. Not immediately, but quickly. You would not have a rental car system anymore. Your enterprise would die. So they are the system to which they belong, the larger system, is an important, we can't say it's an element of this system, but it's an important backdrop to this system. Now, in order to have a rental car company maintenance system, you need trained rental car company maintenance engineers, which means that you need a maintenance engineer training and education system. You need people to teach people to be car maintenance engineers. And this is like biology. So you have carnivores like you and me, or at least I hope you and me. And then you have the things that carnivores eat, and then you have the things which they eat, which are herbivores, and then you have plants, and then you have bacteria. And then you have the environment, which contains inorganic nutrients. Now, no system created by the carnivores, including no car rental maintenance system, can exist without inorganic nutrients and without all the other things which we eat in order to live. And I guess the inorganic nutrient system, which includes the sun, is part of the larger system in which the car rental maintenance system is embedded. Now, that means that in order to understand systems, we need to understand the environment. And so we have an ontology for that, which is called ENVO. And I mentioned it already. It was one of the first things which we added to the Obo Foundry, because biology is so importantly dependent upon environments for all kinds of obvious reasons. So the ENVO ontology, as I said earlier, is a multi-grain ontology. We have molecular environments, cellular environments, whole organism environments. We also have population environments. And environments are something like sites. A site is a place. This room is a site. The interior of this room, this is a breathed environment for people. We can breathe. We can even eat in this room, although there isn't very much food left. We can certainly drink. So this room is an environment. Buffalo is an environment. The United States is an environment. But also the corner of this room where there is a particularly interesting colony of bacteria is also an environment. And so this is another example of a site would be a cave in which a bear is living. But Manhattan is an environment. And now you have to understand that the term Manhattan is ambiguous. On the one hand, it can mean the physical collection of bricks and wiring and plumbing and so forth. But on the other hand, it can mean a site in the BFO sense, which means a hole, a very, very complicatedly shaped hole in which people walk around and sleep and eat and so forth. And then there is the extended Manhattan, which is the sum of those two. And there is also the extended human being, which is me plus my orifices. Because when I get an infectious disease, the infectious agent doesn't necessarily have to be part of me or inside me. It can also be part of or inside my orifices. So words like cave, mouth, nostril, your car, your lab, your bed, and so on are all ambiguous as between Manhattan as a physical collection of bricks and Manhattan as a big hole with an 8. And so there are now several different kinds of environments. That's the environment inside an egg. That's the environment of a snail shell. That's the environment of a cow. That's the environment of a circling buzzard. And the last one is your digestive tract, which is the environment for the trillions of microbiota which keep you alive. All right. So now we're going to define system. So the ENVO already has a definition of system, because so much of what environmental science is about is systems. And I have another handout here. And you should bear in mind that I am not recommending these definitions. I think that they are very illuminating, but that doesn't mean I believe in them. Now, I'll just mention in passing that the ENVO Ontology is the centerpiece of the United Nations Environment Program Ontology Suite, which you can find at the UN website there. And they have something called the Sustainable Development Goals Interface Ontology, which interfaces various ontologies like the ENVO in support of the data collection of the UNEP operations to achieve these Sustainable Development Goals. So, ENVO has a definition of system. It is a material, this should be on your handout, and I guess I should have a copy of that handout to make sure I'm in sync. Do you have a spare one? You have, good. Yeah. So a system is a material entity consisting of multiple components that are causally integrated. I think that this is correct. It captures all of the examples that I pointed to at the beginning. And just to give you an example, take the Manhattan subway system. Actually, New York subway system, I guess. It doesn't really matter. It's made. What is it made of? Well, it's made of railway tracks. It's made of trains. It's made of ticket machines. It's made of people who can drive the trains and maintain the trains and watch over the people. Those people have certain skills, capabilities, in other words. And I think that it's those capabilities, actually, which are the most important, because most easily ignorable feature of a system like the New York subway system. The people who maintain it, the people who keep it running, have to have certain skills, really physically have those skills, and they are part of the system. All right. Now we come to an environmental system. It's a kind of system which has the disposition to environ one or more entities. Unfortunately, we have a definition. Environs means this. A is something like a mountainside with a cave, or a desert region with a pool of water or some kind of water source. And B is something like an organism, and B is in A and causally influenced by A. So not just passing through A, but actually interacting with the environment of A. That's what environs means. And an example outside the biological realm, because there's nothing biological here. So this applies not just to cave birds or cave bears. It applies also to a suitcase, which you lose in the Union Station, which is kept in the Union Station Lost and Found office. That suitcase is environed by the Union Station Lost and Found system. It took me a long time to think up this example, and I think it's very illuminating. But I would say that. And like here again, the system includes people with expertise. So the managers of this system have the expertise. They know how to look after lost parcels. Now, a sub-kind of environmental system is ecosystem, which is an environmental system where we really are dealing with not suitcases, but organisms. And then there are various subtypes of ecosystem. And interesting is an ecological corridor. An ecological corridor is something that doesn't environ the organisms in it, but they just pass through it. They're not causally affected by the corridor. This may be relevant to the Mars mission, because we're going to start with an environment which is comfortable for people. I guess we will continue with an environment which is comfortable for people, but only in a very limited sense. But then around it, we have an ecological corridor which is almost maximally not capable of environing people. And then you land on Mars, and with luck, you will create another larger environment, which is not just an ecological corridor anymore. So an ecological corridor is defined as an ecosystem which bridges two or more adjoining ecosystems and through which organisms may move or propagate. And a habitat is defined as an ecosystem which can sustain and allow the growth of a population of organisms of a single species. That's important. Now we have biome. So biomes are things like desert biomes or mountain biomes. They are specific kinds of ecosystems where we have a specific temperature range, specific water supply features, rain patterns, and so forth, so that specific kinds of organisms evolve and live in those ecosystems. And we use the term ecological community, which is defined on the next slide. An ecological community is a population containing more than one kind of species which are interacting. And a biome is an ecosystem that's determined by an ecological community. And what that means is that the removal of that ecological community would cause the collapse of that system. Now, this is important because this is where failure comes in. Remember, failure is the crucial reason why we're interested in systems in the first place, why systems engineering existed. Failure exists in the biological realm too. So the idea is that the trees in the tropical biome enable all the other organisms in the tropical biome to survive. They determine the climate, they determine the microclimate of organisms that live on the leaves, for instance. And so the ecosystem, which is the forest biome or the tropical biome, is determined by organisms of a certain kind. Without them, the system would fail. And now a community is defined as a collection of organisms connected by social or biological relations. An ecological community then is a community in that sense, but involving at least two species in the same area. Now we can define a microbiome. It's a biome determined by an ecological community of microbiota. So your gut is full of bacteria which help you digest food. Without those biota, you would die. The system, which is your digestive system, would fail and you would die. Okay. And the biome is a system. And what that means is that it includes both the environment and the inhabitants of the environment in this particular context.
So just a quick question. So take the Mars example. There's been a lot of painstaking care to ensure that no organic materials go out of any of the rovers because we want to see if in discovery.
Yeah.
We bring humans there. We've introduced a whole.
Yeah.
How does all that fit into what you just described?
So first of all, it makes me think that there is a kind of dual to the notion of failure, which is the notion of creating a new system by accident in this case. So if the organic material on Mars propagates, which I think it probably would not unless we worked very hard, that would involve something like creation of a new system ex nihilo. But I don't think there would be a system until there was some kind of self-propagation going on. unless, of course, we were helping it, in which case we would be part of the system. And we'd need to be investing a lot of effort and skill and technology in order to make the organic material propagate, I would assume. I'm also assuming that it's going to be isolated from the rest of the environment along many dimensions anyway, not perhaps every dimension. So now, these are some examples of systems. So the solar system I mentioned at the beginning is being outside my purview because I don't believe that there is a notion of failure for the solar system. So it doesn't seem to make sense to say that the solar system failed. If it would just come to an end naturally if the sun burned itself out or exploded and destroyed all the other planets. It wouldn't be a system failure. It would be the end of the system. And we talked about engineered systems. And I mentioned that even a subway system is embedded in a natural system. First of all, it's the natural system of human beings which maintain it, but then also that those human beings need teachers, food suppliers, restaurants, and so forth, plumbers. Now, another example which is being worked on, is that me causing the noise? Oh, is this Jose? Can you? Oh no, he can't talk to me. So Jose, if you hear me, can you mute yourself?
Okay.
Thank you. So trauma systems in hospitals are, I think, a really illustrative example of some of the points I've been making. So first of all, hospitals have trauma systems. They call them trauma systems, and people are trained to work within them to realize the function of the trauma system, which is to accommodate emergency patients who are suffering from trauma effectively so that they are immediately or as quickly as possible taken to the right place and have the right operations performed upon them. The interesting thing about a trauma system is that it has two states. It has the latent state, where the people just have their cell phones at the ready in case there is an emergency. And then there is the emergent state, which is when there are actual trauma patients on the way to the building where the system is located. And we have an ontology for that. And we built the ontology. I didn't build it. One of my co-workers built it. And I'll show you a little bit more of it later on, to solve the following problem. Some trauma systems are very effective. Some trauma systems in some hospitals are very effective. Other trauma systems are less effective. Now, a trauma system involves a certain kind of framework, an organizational framework. If we could build an ontology for those frameworks, and if we could associate the ontology with the actual trauma systems which exhibit these or those features, and then show by looking at outcome statistics that the trauma systems with these features are more effective than trauma systems with those features, then that would be very useful information to have. And so this was, it was an NIH grant which was funded to build the ontology and test it in that kind of way. And there is a paper describing it here, which I will give you the link to also again later. Also, these slides will be made available online. I guess, can you put them on the CIMA site? I will put them on my site also. So, so this is the gut, and there are 10 to the 11th bacteria in your colon. She'll be happy to know. Some people don't have any bacteria in their stomach, but everyone has at least 100. No, some people, everyone has at most 100, according to this. Anyway. So we define microbiome on the basis of our definition of biome. So the microbiome is a biome determined by microbiota. And now we can see the whole thing as it works out in an ontology. So this is BFO in pink. And this is part of the PCO, which is the population and community ontology. So this is a collection of organisms, which is an object aggregate, and then the terms that we just talked about are here, including the sun. And we now have some other relations, not just is-a relations. A habitat is determined by a population, a biome is determined by an ecological community, and a microbiome is determined by a microbial community. So that's the same thing, just focused down to what we're interested in. And this is a fragment, which you can't read very well, of the Ontology for Organizational Structures of Trauma Centers and Trauma Systems. And, well, you can see the green things are instances. They're actual people, actual organizations, actual programs, actual buildings. And then the red or purple things are types. They're ontology terms. So a trauma on-call plan specification, a trauma medical director role, a trauma program, and so on. All right, now some more features of systems which grow more or less naturally out of what I just said. First of all, the trauma system is intervolved with many other systems within the hospital, with the cleaning system, the plumbing system, but also with the surgeons are going to have surgical lives on non-trauma patients. And so you have there's no real line. This is your question about boundaries earlier. There's no real line between the trauma system and the rest of the hospital. And what this means is that the system, I think generally speaking, systems have fiat boundaries rather than physical boundaries. So a fiat boundary is a boundary that is created by fiat. We say, well, this is part of the trauma system, but that over there is part of the plumbing system. But we could have drawn the boundary in a different way because there's no physical discontinuity to guide us. And patterns are the same. So if we have the pattern, which is the pattern of letters on the screen here, then where does this pattern start and stop? Does it include all the margins? Does it include both the shadow here as well as the white margin? There is no one answer to that question. Does it only go as far as the letters, or does it include the spaces between the letters? So that's characteristic of patterns, that they have fiat boundaries. I said already that there are often parts of larger systems and therefore often have smaller systems as parts. Some systems have a self-organizational property, but not all. What that means is that they have within themselves their own repair mechanisms. I guess this must be the case for the Mars lander, that it can repair itself to some degree. It's certainly the case for human beings and for other organisms. It's not the case for product assembly lines in a factory. I won't say anything about the... well, I will actually, yes. An army is a system. It has all the capabilities, it has all the training, has all the features of systems. But now what I think is interesting, and therefore perhaps false, is that when two opposing armies are fighting, they form a system. And what that means, if I'm right here, is that systems can include antagonistic components. And I guess that's true already for a single organism, because we can have pathogens. Our microbiomes can contain not just friendly bacteria, but also unfriendly bacteria. But they're still part of the same microbiome, which is a system. All right. And now let's just, for the sake of curiosity, let's look at some definitions of systems engineering. So this is the ISO IEEE definition of systems engineering. It's an interdisciplinary approach required to transform a set of customer needs into a solution and to support that solution throughout its life. I find that too weak because it doesn't give you any view of the scale of the thing. So this would apply to a single customer who has lost his toothbrush, maybe. But it also doesn't deal with failure. It addresses the positive side, but it doesn't emphasize that the reason why you need the discipline of systems engineering is in order to cope with the phenomenon of failure. This is the INCOS definition. So these are the component parts of systems engineering, and the idea is that the systems engineering integrates all of these disciplines into a team effort, forming a structured development process that goes from a concept to production to operation. So I guess that would cover the Mars mission. And then Seebeck has a definition, which I guess is really just along the similar lines to the one that we just saw. This relates to the earlier definition in that it emphasizes the ongoing intertwining of system requirements definition of system design, which means that we have constantly to keep the system alive and awake and functioning. And that again would apply to the Mars mission. So the systems engineering role in the Mars mission continues from beginning to end, where the engineering role in manufacturing applies really only at the beginning. Once you have the production line going, then you need maintenance, but you don't need more engineering. This is the ISO page where you can find 8 different definitions of system, which is a pity because ISO should have one definition. That's the whole point of having an international standard. No. Okay, now something went wrong here. Sorry. Maybe we can have questions at this point.
Yeah, I'll just skip the mic. I have a question. Isn't there a problem with having, as you gave the example of, 2 different armies butting against each other? Couldn't that not be a system because they're not actually integrated? Like, isn't integration like the necessary part of part of the definition, and they're lacking at alignment?
So I'm not an expert on that kind of question, but it seems to me that the very lack of integration in that context is relevant to the system. So if they were integrated, that would mean that they were being nice to each other. And the whole point is that they're not being nice to each other. That's part of the system. This is not an engineered system. Each individual army would be an engineered artifact, something like an engineered artifact, engineered social artifact. The war itself is a natural system. But because they are fighting each other, that means they are causally integrated.
I have a question. It has to do with the inclusion of the notion of the environment of the system. In our words, just to make an analogy to that, we're dealing with information, right? And we have directed observational capabilities, sensors and things, humans in, that I call focal information in my own speak. But those information systems also incorporate context, or is to textual information. For instance, in military affairs, how you interpret the observational data, focal data, may depend, for instance, on a political climate, which is so here. What I'm wondering, I see the notion of system as something, let's say, controllable, whereas notions of environment to include in our case, we worry about weather effects, for instance, on sensors. But those are out of our control. So they are not in our, we're from the space of thinking, so, or notion of the system. Yeah. So it seems to me that those definitions that have implications, including considerations of an environment, so to say, are, I think, questionable in the sense that environmental things in many cases are not in your control.
So I think
kind of take your best assessment of what the impacts might be, but it muddies the definition of it.
Okay, so first of all, I think this is a very interesting choke point here. So most of the standard definitions of system, including the ones created by Inkos and Seabock, allow that there are natural systems, and mention the solar system in that connection. And we're certainly, the solar system certainly is not under our control, but it is very much like an engineered artifact from some perspectives. We might build one. Secondly, digestive systems look very much like some engineered artifacts that you might find in a food processing plant or somewhere like that. And also, increasingly, systems inside the organism, which are natural systems, are being brought under control. So the more we have implanted devices in our bodies, the more that means that we are using engineering skills in order to control biological processes. So I don't think that there is quite such a sharp line between the two as you suppose. Moreover, I would say that, and that actually this brings me back to one of my first points. The reason why we have systems engineering is because the DoD pays for it. Why do they pay for it? Because of war. Or because bad things happen when you have military operations going on, mainly because of war. Now, so you have systems engineering because of war. That doesn't mean war is a system. But if you have two armies fighting each other, then I think you have something like a natural system. One side is going to win, we assume, other things being equal, other things not being equal. But as I say, that's not something that I am particularly confident about, whether if you have two armies engaged in a war, then you have a single system. There are all kinds of things which point in its favor, though. A chess game, for instance. It looks a bit like a system, and it's not in our control. We control it, but neither of us controls it alone.
Well, okay. As I say, it's the system engineering process. I go back.
Yep.
Love. We get the phrase now,
Yeah. And the maintenance of those things.
Applies controllability.
I agree. The goal of systems engineering is to solve people's problems, complex problems, in such a way as to create products, which I assume are going to be called systems, engineered systems, which will address those problems on an ongoing basis. So the thing which is created, the system will address those problems, not just today, but also for as long as the need is present. Now, a war or a conflagration between two armies is certainly not a system in that sense. The question is whether it's reasonably called a natural system. So I accept that there are engineered systems. You don't accept that there are also natural systems. And I think we can agree that systems engineering is about engineered systems, and we are trying to define what that might mean. And part of that definition involves defining what system might be. Now, I think that one of the clearest examples of a system is the digestive system. Now, this is the point we reached in Washington. And then the next question was, well, if the digestive system is a system, perhaps the whole organism is a system. And if the whole organism is a system, then there wouldn't be any disjointness between object and system. And so you could have a washing machine be a system. And a washing machine contains many parts which are integrated. They work together to achieve a goal. They need maintenance. Why wouldn't you say that a washing machine is a system? And here I say no. And a single object cannot be a system. It can have systems as parts, but it can't be a system. And BFO is actually neutral still, but there will come a point where BFO will have to make a decision on this point and determine how to classify systems. Yeah.
I guess I'll just try to project from then going up the mic. Is with that mindset of the washing machine, are you saying then that an aircraft or a power plant is not a system?
I would have to say that for the aircraft. The power plant is a bit, if it's a small self-contained power plant, then no, it can't be a system. If it's a larger collection of buildings and structures, then it might be a system. According to the intuitions which are dominating in my weak soul, ontology is an important contribution to mitigating a certain kind of failure, namely the failure I described with the Airbus wiring problem. So it will, to the extent that those kinds of incompatibilities of terminology and of database design are contributing to larger systems failures, then ontology can help.
My question is actually, have you defined?
So the question is, I have used the term failure. I claimed ontology can mitigate failure in one particular way, but have I defined failure? Now, I first of all said that the solar system could not fail. It can cease to exist, but it can't fail. So there must be some distinction between failure and ceasing to exist. And I guess failure would be defined as something like this. A system fails if it breaks or deteriorates or decays. In other words, it might be a slow or immediate change, which is such that it is irresolvably no longer able to achieve its purpose. And so the question is, how does that differ from death? And I guess when the digestive system or the cardiovascular system is the cause of death for everybody. When the cardiovascular system fails, then we die. That doesn't mean that we fail, because we're not systems. We are organisms which have systems as parts. And when one particular system, namely the cardiovascular system, fails, that means we're dead.
Right, so the thing is that when the system just no longer is able to achieve.
Yeah. Yeah. And I'm not actually sure. Let me just push this one bit further. The solar system cannot fail because the solar system has no purpose. The digestive system has a purpose. The cardiovascular system has a purpose, but the solar system doesn't have a purpose.
So I think this is getting into ontology.
I don't want that, but go on. Yeah, good. Neither do I. Yeah. Okay, so then let me try and push the can of worms a little bit further. So what is the purpose of a biome? What is the purpose of we know what the purpose of the microbiome is. It's to keep us alive, roughly speaking. What's the purpose of a biome? The desert biome or the forest biome? But it doesn't sound to me like it has a purpose. So I'm still not in good shape. So, but can the forest biome fail? I think probably, well, yes, it would fail if you removed all the trees. Go ahead.
You wouldn't follow us. I was just gonna continue and say, is the purpose to perpetuate itself? So then it could fail if it failed to.
Yes, that's the actually the favorite approach of biologists, that the purpose of all organisms is to perpetuate their genome, basically. But the biome isn't an organism. It's a certain band of ecological variation realized in a certain place on the planet. So that wouldn't work for biome. It would work for actually no, it wouldn't work for anything. So organisms don't have purposes. Oh, you're saying organisms do have purposes. So in other words, organisms could fail if they die. But no, an organism dying isn't necessarily failing, because it may have perpetuated its genome. Some organisms die in reproducing. So dying in that case is not a sign of failure, it's a sign of success. But still, it satisfies your criterion. So I cannot say that organisms do not fail because they have no purpose, because you will come along and say the purpose of organisms is to perpetuate their species or their genome. I would say organisms still cannot fail because organisms are not systems, and only systems can fail. Because I'm interested in the... Yeah, but that... Yeah.
Then that forest no longer continues to function as a forest, and it failed.
So there are some people who think that environments have value, innate value, and that we should preserve them. We all think that our own environment should be preserved, but that's because we all desire to preserve ourselves and our offspring. I think the people who think that environments have to be preserved are making a mistake. And so I still don't see a reason for believing that an environment can have a purpose. And they are systems. So an environmental system is a system. So it should be the case that an environmental system is in the market, at least, for suffering from system failure. But it's not. It's like an organism. It just dies. It's like the solar system. So we have two kinds of systems. And this is how I started off. Two kinds of systems. Those that can suffer failure and those that can't. The decimal system can't suffer failure. The solar system can't suffer failure. Environmental system can't suffer failure. And that I'm going to write that down because that's something I hadn't thought about.
Does that break the all sum?
No, because nowhere did I say all systems can fail. I did not say that. No. Only engineered systems, because all engineered systems have purposes and all engineered systems are systems. And the definition of failure is being a system which is irresolvably not able to realize its purpose, or being a form system. Yeah.
All this would be helpful if you define the purpose. So
for this purpose, I'm going to settle on the word function. So organisms don't have functions unless they are selectively created bacteria or similar organisms. We're just here by accident. And the solar system doesn't have a purpose. The tropical biome doesn't have a purpose. Function.
indeed.
Has a... Wow, and now we're getting interesting. Yes, it has a function. I'm using the word function to mean purpose, just to see how it flies.
Symbiotic relationship has a purpose, but not the microbiome is just there because
I'm talking about the microbiome in situ always. So there are microbiomes outside, free in the atmosphere, so I understand. And there are certainly microbiomes in ponds which do not have a function. But the microbiome in your gut has a function. Yeah, it doesn't matter how it got there. Yeah, but Yeah, you have to work hard to keep them in their functional place.
Maybe I'm misunderstanding Clifford's, but how can the microbiome touch well?
I never used the word intentionality or any similar word, and that's one of the reasons why I withdrew a little bit from the word purpose. So, in order to have a function, you do not need intentionality. The heart of dinosaurs had a function, namely to pump dinosaur blood. But there was no intention, unless you allow God to have been around creating dinosaurs already. Yep.
This is a Trump market question. You may,
Yes.
I take you make same station and this is system.
Yep.
Like the system and operating system.
So, functioning, I would say, actually, that's also a good question. So I talked about some systems being in a latent state, and the trauma system is a good example. There is a latent state, and then there is an operating state. It's not the case that all systems have latent and operating states. The hydraulic system in your car has a latent state when your car is idle, or switched off, or never even released from the warehouse. All engineered systems have a latent state? Is that true? I don't know. Could you switch off the Mars mission for 3 weeks and then switch it on again? No, you couldn't. So nearly all engineered systems have a latent state. And then they're idle. They're not functioning. And what that means is that all the components within them which do have functions are not functioning. Now, that's probably not quite true. Some of them will still function. For instance, even if you switch off your car, the exterior membrane is still protecting the car from the environment. So it's still exercising its function. But that's a very special case of functions which are realized always, fences and skin and membranes generally.
The reason I ask is, so the classic in the case of function and functioning, and the function is a...
Yep. Thing is a process. Yep.
An idle system, I would think would be like a current, right?
Yeah, the system, a car idling isn't a current. It's just a very, very boring current involving no change at all, just sitting there. Nothing turning over in the engine. There'll be at the subatomic level, there'll be a huge amount of activity, but at all the levels which are important for us, there'll be no activity at all. So I agree. It's not a state. It's just a very, very, very boring process. No, all systems have functional parts. I think that's true. No, the solar system doesn't have functional parts. All engineered systems have functional parts. Many biological systems have functional parts. All systems have activity. But some systems have a latent state when the activity ceases. Latent period when activity ceases. I think that's what I want to say.